Right, this is a quick question. Right, so from the information here, what is the hematite? Well, the hematite is the iron ore. Just using a bit of information there. It's combining the information from the question above with the diagram below. Limestone, what's another name for limestone? Well, calcium carbonate is limestone. Okay, and the formula for calcium carbonate is down there. Okay, so it's using the information from different parts of the it's reactants from different parts of the question. So you have to read the whole question. That's the technique. Okay, so here we are. We've got a burning combustion there. That produces a heat, so that's the first thing. Neutralization reaction. So we've got a metal oxide and a non-metal oxide coming together. That's neutralization. Remember, metal oxides are basic or bases, and non-metal oxides are acidic. That's what they're expecting you to know. Acidic. So that's neutralization. Decomposition, finding out the decomposition reaction, taking one substance and breaking it down into heat into two substances. And the reducing agent is carbon monoxide. So the equation that produces the carbon monoxide is the equation C. Okay, that's a process of elimination. The molten slag, just looking at the diagram, just have to look at the diagram, it tells you what the other thing is. You might know the formula for the name for the molten slag is calcium silicate, but just look at the diagram, it's not a raw material going in. Okay, I think I miss. So you can't extract aluminium like this. Why is that? It's too reactive. So let me just erase that answer. I put the wrong answer in the wrong part there. So why is it different method? Why is a different method used for aluminium? Because aluminium is more reactive, so you need to use electrolysis to extract it. Electrolysis uses electricity, which is very, very expensive. So the cost of the electricity makes aluminium prohibitively expensive. That's why they ask you to recycle it. Coke is used in the blast furnace, contains carbon. Carbon is used also in the extraction of aluminium. It's used to make the electrodes, anode, and also the lining, which is the cathode, but you just put down the electrodes. That's fine. Why? Because it's made of graphite. Graphite is a good conductor. So write the two equations for it. So aluminium oxide, which is Al3+, plus 3 electrons is going to aluminium. And the oxide ions, which is O2-, is going to O2. So you're going to need 2 oxide ions. And that's releasing 4 electrons. Bit of electrolysis there. So you want to measure 25 centimeters cubed of sodium hydroxide. You'd need a pipette for that. Has to be a pipette, anything that's accurate enough to do that. Okay, what's the colour change for the phenolphthalein? Well, it starts off in an alkali and goes to colourless, which is because it goes into an acid. So it's the change of the reaction in the reaction vessel is alkali to acid, so it's going to go from pink to colourless. So you need to know your phenolphthalein indicator. Why is phenolphthalein better indicator than universal indicator? Well, you've got a clearer colour change because there's only 2 colours that it changes from, colourless to pink, whereas it's much more difficult with universal indicator because you've got a range of colours there. It's not just about, it's more accurate. It's more accurate because there's only 2 colours. That's what was the answer to the question there. There's only a change between the 2. Right, next one, reading the burette. A lot of people get this wrong still because they're expecting to read from bottom upwards. You're thinking it's a measuring cylinder. It's not a measuring cylinder. Remember, a pipette tells you how much you've added. Okay, it's got the tap at the bottom. Okay, so got to read that one there. That's 24.1, and it's between the lines. 1.5. The beginning is 2.3 and it's on the line, so it's 2.30. It's got to be to 2 decimal places, your answers. You can't just put 2.3. It's not showing the precision you're working to. Common question, common error. So it's 21.85. 1 mark for each. And if you're not doing it to decimal places, you can only penalise that once. So concordant results need to be the closest together. Plus or minus 0.1 is what we define as. So there's only those two there. So only those two you can use in your average. So 1 mark for the 2 ticks there. Then show how you're going to work the average. 26.3 plus 26.4 divided by 2, giving you 26.35. 26.30 plus 26.40 divided by 2 is 26.5, is it? 26.350. So here we are, a tough little equation here. We've got sodium hydroxide, 3 lots reacting with phosphoric acid. So that's going to affect our ratio here. So calculate the amount in moles of sodium hydroxide. Remember, they give you the details there. But remember, the volumes are in the wrong units. They need to be divided by 1,000 to get them into decimeters cubed. So we've got a concentration of sodium hydroxide. Concentration times by volume equals number of moles. So it's going to be 0.18 moles per decimeter cubed times by 25 times 10 to the minus 3, because you're dividing it by 1,000 to get it from centimeters cubed to decimeters cubed, which equals 0.0045. If you get that, you get 2 marks. If you didn't get that, but you got the equation right, you get, or the information right, you get 1 mark. So you've just got a keying error, you get a mark there. Right, the tricky little thing here, you need to work out the moles of phosphoric acid. You use the ratio from the equation. So if you look at the equation above, the ratio for phosphoric acid to sodium hydroxide is 1 to 3. You know the moles of sodium hydroxide is 0.0045. So you divide that by 3, which is 0.0015. Okay, just 1 mark. Using the ratio from the equation, calculate the concentration in moles per decimeter cubed. Once again, problem here is they're giving you a value in centimeters cubed, so you need to divide that by 1,000. So you've got number of moles divided by the volume. So 0.0015 divided by 28.3, but it's not 28.3, it's 28.3 times 10 to the minus 3, which equals 0.053. So 2 marks for the answer. If you didn't get that, 1 mark for the right equation. So if you've got a keying error. Copper and metal are metals. Copper and iron are metals. Typical properties, they have a high melting point and good electrical. So you need to draw the structure. So you need to draw at least 5 cations in the lattice, in a nice regular lattice, as regular as you can make it. I'm rushing through this. And remember, they're cations, so they're positive. So I'm just taking the time to put that in there. And then in between the lattice, you need to make sure you put your delocalized electrons. Now you can use dots, quite big dots, but not too big. Okay. Or you can use E or E minus. Okay. So you need the cationic lattice, or lattice of atoms, or positively charged ions. So I've got to put down cationic lattice. Okay, you've got your delocalized electrons labelled. That's also 1 mark. But you've also got to remember you've got roughly the same number of delocalized electrons to Oh, it's terrible. Oh, let me write this down here. You can have roughly the same number of delocalized electrons to metals, cations in the lattice. Why? Explain why metals have good electrical conductivity. Why? Because they have delocalized electrons. That's 1 mark. Okay, but you need to say that these delocalized electrons can flow through the lattice, or can move through the lattice. So it's not just about delocalized electrons, they can flow through the lattice. Usually that's worth 2 marks. Okay, so here we are, we've got some lead bromide. At the beginning, the lead bromide doesn't conduct electricity. Lead bromide is an ionic substance, and the ions are not free to move when it's solid. You can't just put electrons, no delocalized electrons. It's because it's an ionic substance. When it's solid, the ions are not free to move. Okay, this is oxidation. Why is it described as oxidation? Well, because you've got loss of electrons. Remember the oil rig definition. Write an ion equation that electrode B. Now, electrode B is negative. You look at the diagram above. So therefore, it's the 2 plus ions there. The lead 2 plus ions. They're gaining electrons. Okay, they're being reduced there to form lead metal. What would you see? What would the appearance be? You'd see lead metal, which is a silvery grey substance. Okay, silver grey metal forming. And you should have seen that demonstration in the laboratory. And that's it.